Okay, let's start today's session. I hope you're enjoying the weather. Uh, Beside the allergy reactions, it's good. Yeah, and let's start our last topics of the course. So we are gonna basically end our lectures with this topic. The topic is fault right through. Uh, Before I start, is there any question for the previous sessions, the transient analysis? Because far right two is basically a byproduct or like, a one regulation over transient analysis. Is there any question about the previous topics? Guys in the Zoom? No? Okay. So let's start today. Now, fault right two. If I wanted to like describe fault right through in a very simple statement, this is most of our like regulation wise for the inverter based resources specifically, and it would define how long and how far each inverter have to tolerate the transient disturbance, specifically voltage sags or voltage swells, okay, before they are allowed to trip out of the grid. Because we already talked about that, when we have a fault, the normal kind of reaction of every component in the grid is to protect themselves. Basically, they want to break the connection from the grid, disconnect, and protect their own circuit from that disturbance. Okay, but if this is allowed, basically, with every disturbance, we have a chaotic behavior of those components, and especially when we're dealing with the resources, and most importantly, like inverter resources, that they have a very fast control system. Okay, if we allow them to break from the grid easily, then we would have a severe problem of stability every time a transient incident would happen. Now, why this is important for uh, most specifically inverter-based resources. Now, most of the inverter-based resources are considered as distributed energy resources. Okay, DERs, distributed energy resources. Okay, one of the characteristics of distributed energy resources is that they are a bidirectional power flow. They have bidirectional power flow. So when you have a distributed energy, the interaction of the DERs with the bulk grid is bidirectional. So sometimes they add power to the bulk grid, sometimes they receive power from the bulk grid. And it's both active and reactive. It's not just reactive. Okay, so for example, one of the new application of that electrical vehicles, the EVs, is that this is a new idea. They wanted to use it as energy storage. So, for example, when someone plugs in their car into the charger, okay, through the night, the grid might use that charger as a generator rather than as a load if there is a need of energy. You know what I'm saying? So it's a bidirectional. This is one simple example. This is a bidirectional flow of power, which is different from the conventional scenarios. In conventional generators, like a rotary machine, if you have a rotary, like a synchronous generator, that would act as a synchronous generator. It wouldn't change to the motor in the middle of the performance. So it's always going to be generated. So it's a one directional, monodirectional, powerful, always inject. But DERs are not. That being said, mathematically now we have both positive and negative power in the DER. Before, we only deal with the positive value for P. Now, there is a chance of negative value for T or for P. Now, what are the challenges that DERs, which basically work with the inverters, or to state in a better way, inverter-based resources are mostly DERs, distributed energy resources. The challenges that they bring is that, first of all, they are non-dispatchable resources. What that means? You probably heard about the central control system of a power grid. The control room that defines when and how much each generator have to inject power into the grid. So they would keep the balance between demand and generation. This is what happens in a conventional grid. But in DER, it's hard to manage. If it's not impossible, if we don't want to say it's impossible to dispatch DERs, it's a very hard kind of like thing to do to control those resources. Another part is that the most of the DERs, as we said, are the inverter-based resources, like for example, the wind generation or the solar power, okay? They are vastly influenced by weather condition. So it's not like a synchronous generator that the control system could mandate a certain amount of power out of that generator, and there is like a solid capacity for a generator. No, in power system like a solar, the maximum capacity that each generation site could deliver to the system is depending on a weather condition. So it's not a solid cap. It's not a reliable, measure to be controlled. And another part is the stabilization solutions. Okay, we already talked about how inverters and inverter-based resources would affect the power flow analysis and transient analysis. We saw how integration of the inverters changed the Jacobian matrix in power flow. Okay, would add a huge amount of complexity for analysis and to keep the system stable. Okay, in transient analysis, we saw that when we integrate the IBRs, we are going to have to deal with a nonlinear, extremely complex model, which basically means, okay, if we wanted to like stabilize our system, now we have a very hard time to first of all, to analyze the system, find the weak points, and now optimize the situation to avoid unstable region. It's going to be a harder task to do. So these are the challenges that we have. Now, why we are talking about these problems? These problems in DER are basically, in general, are going to impact the upstream generation. What I mean by upstream generation, I mean the bulk power grid, the main grid that we have in our system. Because of those challenges and those differences that they have with the conventional resources, adjustment of the output in such resources are going to be very hard to do. We already talked about that. There is like a dependency on weather. There is nonlinear behavior, nonlinear model. If we cannot adjust the power or adjust the power flow precisely and in a stable way with the bulk grid, what's going to happen? Either we are low in a generation compared to the demand, okay, which in active power means the frequency would fall down. You remember that, the relation? And in a reactive power means the voltage will fall. This is one scenario. Another scenario of not being able to adjust the power or adjust the interaction of those DERs with the grid is that we have more generation than demand. Again, in active power, that means we are going to have an increase in the frequency. And from the reactive power perspective, we are going to face an increase in a voltage level, which both of them were, all those consequences were something that we wanted to avoid because it would affect the stability of our system. Now, in a steady state, when we have a very kind of like normal system operation, the system is in the equilibrium point, the power flow is stable, we don't have any problem because everything already synced up with each other. Now, the problem happens when for any kind of reason we have a disturbance. Okay. That being said, this is the reason that I said the fault right through concept is tied to the transient analysis. Because we are going to talk about the events when we have a disturbance. One of the most common disturbance in the system, okay, the fast disturbance in the system is the voltage faults. Voltage faults doesn't mean always a voltage decrease or voltage sag. Sometimes a fault could increase the voltage. Anyone can tell me an example or heard of an example of when a fault actually makes a swell in a voltage, an increase in a voltage? Anyone heard about that? Like we have a short circuit, but instead of increasing the voltage in our three-phase system, instead of increase of the voltage, we are going to face, instead of decrease of the voltage, we are going to face increase in the voltage in some places. Now, I'm going to give you the example. You can search on that. When you have in a three-phase system, when you have a fault of two lines, two of the phases to the ground. So, for example, we have, this is our three phases. Same amplitude, 120 phase shift. If two of them get connected to the ground, so we have a fault, what happens is that now the two phases are here, but the amplitude, the circle, remains solid. So now we have a higher voltage because the reference points are now moved down. We have a higher voltage in our third phase. So a short circuit in our system created an increase in the voltage in a part of our system. Now, that being said, okay, we also have faults that open circuit system. And that's, I think, is more kind of like understanding that open circuit, okay, we have a chance of over voltage or voltage swells in our system. Now, this is one aspect of that fault. If a fault happens, it's a Ohm's law situation. If we have a short circuit, what that means? That means we face a very low resistance between a high potential to the ground. That's what the short circuit, or high potential and a very low potential. Or to be very kind of like precise or like rigorous between a very different potentials. We have a low resistance connection. If we have such a thing, what is the result based on the Ohm law? We have a huge potential difference, low resistance, meaning we are going to face a huge amount of current. Okay? When we have a huge amount of current, what's going to happen in our system? What was the result of having high current in our system, in a resistive system? Anyone can tell me? Heat. Because we are, if we increase the current, that means we are increasing the power loss. That means we are increasing the heat. And the heat is going to burn down our equipment, our insulations. Okay, so if a fault happens, we are going to have voltage sags, voltage source, equipment damage. Now, we have to monitor the voltage, okay? Monitor the voltage constantly in order to find out if there is a fault happening or not. Because we see the consequences of a fault is very harsh. So we want to detect them before it's too late. And what happens when we detect them? When we detect the change or deviation in voltages in our system, is not always fault. So we have to distinguish regular voltage disturbance or fluctuation from the harmful disturbance. One of them being fault. How we could do that? By a protection system, by defining a logic. Okay, if I have a deviation higher than a certain threshold, that means I might face a harmful incident. So I need to protect the system against that harmful incident. Or if I have a relatively moderate voltage difference, but it happens for a very long time, that means, again, something is wrong in our system. It's not a fast transient. It's something happened. The system is changed. So I need to protect the system or the components from that, the consequences of that change. This is when the protection comes in. Now, what happens when the protection comes in? Ideally, protection sees a fault or any disturbance and reacts passively, because the default of the protection is to protect the system or the component connected to the system. But that's, if we just formulate our response to a disturbance based on an ideal protection, that means any harsh disturbance, even if it's very short time, it would result of the protection activating and disconnecting certain component, which also are going to affect our load demand balance, meaning it would going to affect our stability of the system. So in such a situation, protection, instead of helping the system, is actually causing instability by cutting out component when is not absolute necessary to do that. Now, before we talk about that, how we could deal with that situation, let's go over the faults. What are the faults? Because most of the most important cause of those disturbances that we are going to talk about are faults. When there is a short circuit or open circuit in our system. Now, faults are divided into a certain categories. The first categorization is based on the nature of the fault, as we said. Either it's an open circuit, okay, something got disconnected, some sort of like maybe a transition line is open, okay, by accident or by mistake. The other category is short circuit that I assume that you understand faults, or like your definition of the faults is mostly about the short circuit. What you learn is that, okay, you define the faults in a system as a short circuit. So first point that I wanted to say is that not always fault defines as a short circuit. Sometimes it's an open circuit. Okay, now we have a three-phase system. So when we have an open circuit, it could happen in one phase, two phase, or three phase. So an open circuit fault could be a single phase fault, two phase fault, or three phase fault. That being said, open circuit happens compared to the short circuit happens very rarely. Okay, that's why the common understanding of a fault is short circuit, because most of the faults are short circuit. Now, in the short circuit category, we have two types of faults. We call them symmetric faults and asymmetric faults. If you remember the example that I made for a fault that would cause an overvoltage or a voltage swell, we saw that when the fault happened on our diagram, instead of having a very symmetric, balanced three-phase system, the symmetric of the shapes of those three phases got disturbed. So now we don't have a balanced, symmetric kind of like three-phase system. Based on that, these categories of symmetric faults and asymmetric faults is based on that visualization that we saw. Now, symmetric faults, okay, I think it's easy to kind of like expect that the symmetric faults are gonna be always three-phase. Why? Because if we have different situation between all those three phases, that was our initial situation when we had no fault. If anything happened to all three phases, all of them are gonna change similarly. So we're still gonna have a different version of our symmetric balance system. So if we have a three-phase fault, meaning the three phases are connected to each other, or three-phase to the ground, meaning all the three phases are now connected to the ground, we have a symmetric fault, because what happens to all the three phases. Is that clear? Now, in asymmetric faults, we don't have that luxury of symmetry or balance in our system. The asymmetric fault could be a single line to the ground fault when one of those three phases are short-circuited to the ground. Okay, which you can easily assume that, okay, if one of these, like for example this one, connected to the ground, that means zero is moving here. So now we have an asymmetric two-phase. Is that clear? we could have line-to-line fault, meaning these two connect to each other, for example. Again, it would disrupt the three-phase balance. Or we could have a double line to the ground, the example that I made earlier. Okay, and it again would have an asymmetric result in asymmetric fault. Are we clear about the categories of the faults? So it could be open circuit, short circuit. Short circuit could be symmetric or asymmetric. Each of them has their own categories. Symmetric is always three-phase. Either the three-phase connect to each other or connect to the ground. So it happens to all of them. In asymmetrics, it happens to either one or two of the phases. Now it could be line to line, so phases are connecting to each other, or line to ground, one of the phases connect to each other, or two line to the ground, two of the phases connect to the voltage zero or ground. Are we good? Just make sure there is any question in the Zoom. Okay. Now that we defined all the faults and we said, okay, what are the challenges that we might face if the faults happen or the fast transient happen? We said if we let the protection, which is there to deal with those faults, works ideally. That means every time that faults happen, the second or the instant, because second is not a good, because we are working in a millisecond kind of like scale. The instant that the protection would detect that fault, ideally it should break or clear that fault, break down the connection, all the connections to that fault, isolate the fault, save all the other components in our system. But if we let that happen, for DERs, we are going to have a huge problem of instability because every time a fault happens, even if the fault is not that harsh and the system can work through that fault, either the voltage deviation is too low or the duration of the fault is too short. So we are capable of tolerating that fault. If we don't consider that, every time any incident happens, the protection system of the inverters, which is much faster than the conventional generator, would seize the power, and not just seize the power, would disconnect the inverters from the grid because it wants to protect the inverters. And if that happens, as we said, that means anytime an incident happens, we are going to lose a huge amount of generation. Power balance is disturbed, system goes to instability. Worst case scenario, blackout. Now, why this is important? Like you can search on Google or in the NER LSAR websites, NER, National Laboratory of Energy Resources. Okay. Now, in NER site, you could find tons of reports of such accident that happened. Like basically every year, when we have a wildfire in California, this thing happened. Inverter would trip because wildfire would disturb some of the transition line. There is going to be a short circuit, and the inverter would detect that fault and immediately disconnect from the grid. So now the power and demand, the generation and demand balance is disturbed. So all the other generators are going to be overloaded significantly. And when that happens, they are going to kind of like get overloaded. And when the generators, even the conventional one, get hugely overloaded, it would damage it. So basically the protection of those generators would cut them out. Eventually, this cascade of disconnection of the generator would end up in a blackout, which is basically means the whole grid is down. Okay, it's mostly like I think I don't know about the last year, but at least the last 5 years before that, I see the incident happen in California every year when the wildfire happened. So how we could deal with that? In order to deal with that, we need to develop a new regulation, a new control kind of like method to overcome that problem. That control method or regulation is fault right true. So the definition of the fault right true is to enhance, what we wanted to do is to enhance grid stability. How? By continuing operation during a disturbance. So what we are going to do is that, okay, the system should remain online for a minor or tolerable disturbances. So that means it's not just, when we want to talk about the transient, is not just detecting if the faults happen or not, or if the incident, what kind of incident happened or not. We also have to recognize if we can tolerate through that incident or we have to clear that out. So now we have two conditions. The second condition, we call it fault right true. What would be the controller role in fault right true? As we said, the first action is the detection of the fault. So we have to find out when the disturbance happen. The first thing is that, okay, we find that disturbance. Now, the fault right true would change the controller threshold, okay? It indicate another threshold for the protection system in the controller. So if the level of the disturbance is lower than a certain point, or the duration is shorter than a certain time, controller should not seize the power or disconnect from the system. It should remain injecting power, even if it means there is a rush of a fault current and now the inverter had to kind of like inject a rush of a current or a huge amount of reactive power in order to help the system to tolerate the fault. Okay, so that being said, fault right true situations is not inverters working regularly. They are gonna respond to the fault, and they are gonna have to increase their current or reactive power injection in order to answer to the fault, help the system to overcome the fault. What it means is that fault right true made the inverter not to disconnect. Okay. Now, there are several techniques for fault right true. Some techniques are passive, meaning it's simply we delay, okay, for the reaction to each incident. So instead of instant reaction in our ideal protection scenario, we say the protection system, okay, you find the fault, wait for a few milliseconds or like a microseconds, or like wait for 2 cycles, then react. If it's still over there, if the fault is still over there, then you can disconnect. Okay? Or we define as different threshold for the fault. So like regularly we say, okay, if there is a 0.1 deviation in frequency or a certain like threshold for voltage, for deviation in voltage in the conventional system to define there is a fault happen, we simply change that threshold and tell the protection system, okay, don't be basically a sissy pan, tolerate more. Okay, so this is kind of like the passive, the intention of like the how the passive system works. We could have an active strategy, which now we are implementing a real-time response, but that real-time response needs a more complicated control kind of like structure. Or if you wanted to like precisely say, it's a pattern recognition in order to exactly identify what's going to happen. It's not just yes or no for the fault happened or not. You have to find out, okay, what happened exactly, and based on that, define the reaction. So we actively change the control system or the thresholds for the protection based on what actually happening out there. So it's not just manipulating the threshold in passive system, you are changing threshold, but the threshold is constant. In active system, real-time control system would define the threshold. So the threshold for a voltage could be different from 1 second to another. Same for the frequency. And we have to align with the situation. Now, we always said, okay, there is a threshold, what's going to happen? There is a fault, the voltage is going to swell or sag. We have to compensate that. There is a threshold of the ideal situation. We want to define a threshold for more toleration or like fault right through activity. But who defines those thresholds? How we could define those conditions? If anyone want to like haphazardly choose their own, then we are also have a chaotic behavior in our system. So we have to come up with a certain specific condition to regulate those path right through performances. Now, to do that, we are going to have to define the standard for voltage deviation through the time, so the level of the deviation and the duration of that level of the deviation, okay, for both voltage, and since we are talking about the voltage, and it means reactive power. So both voltage and reactive power. Are we good? Now, if we want to change the reactive power in order to respond to the system, the first thing that happens is that the ratio between active and reactive power would change because our capacity as apparent power is constant. We can generate more than the capacity of the generators. Okay, so basically, when we say we change the reactive power, that means the portion of active power is now dedicated to the reactive power. Meaning the power factor would be disturbed, which also we don't want that. So when we wanted to regulate that, we have to consider voltage, reactive power, and power factor. Are we clear so far? Any questions, Zoom? No? Okay. Now, one of the regulations on fault right through or voltage fault right through, for to precise, is the standard of IEEE 1547. There are other regulations and standards out there, but this one, I chose this one because it's the kind of like the most famous one, most popular one, and the most precise one. Okay, so it's if you read the standard, it would gives you a very good intuition about what we're talking about the fault, what is the fault right through, and what we are talking about the instability of the voltage, even when the incident happens. Now, The IEEE standard would define those threshold for toleration of inverters into our system. As you can see in the slides, the IEEE categorize those voltage right through into the high voltage right through and low voltage right through. Based on the graph, you could easily find that, okay, high voltage right through means voltage slow. Low voltage right through means voltage sag. So in high voltage, there's an increase in the voltage. Disturbance is an increase in the voltage. In a low voltage LVRT, we have a decrease in the voltage, whatever incident happens. Now, in our situation, as you can see, the maximum amount of voltage sold by defined by this IEEE is 1.25 per unit, meaning whatever your nominal voltage is, you have to tolerate 25% over voltage if the over voltage only lasts for 200 milliseconds. If it's longer than that, you can disconnect from the grid, protect yourself. But before that, you need to maintain your connection and contribute to overcoming the fault. Okay? Now, same kind of concept goes toward the LVRT, the low voltage. We are going to define, you're going to see the definition of the how far you have to tolerate the voltage for the time and the values. There's a table actually for that. This is the table. If the voltage, like incident happened, our new voltage is between 0 to 45% of the nominal voltage, the one before the fault. Okay? You have to keep up for 160 milliseconds. After that, you can disconnect. But before that, you need to contribute, the inverters have to contribute to overcoming the fault. Now, there is another margin, 45% to 65% of the nominal voltage. You have to remain connected to the system and contribute for 0.32 seconds. Pay attention to the units. The top one was millisecond. This one is second. Okay, so actually you can easily, this is not hard to relate. Now, if the voltage drop caused the after fault or duration fault during fault voltage being 65 to 88% of the nominal voltage. By nominal voltage, I mean the voltage before fault, okay? You have to remain at least for 2 seconds. After 2 seconds, if the fault is still there, you can disconnect. Now, if you have 88% of the nominal voltage up to 1.1, okay, so 12% minus 12% plus 10%, okay, minus 12% plus 10% deviation from nominal voltage. We don't consider it as a fault. You have to keep going even if it happens for infinite amount of time. So above that 10%, up to 20%, we define it as an incident, but you have to stay connected for at least 1 second. More than 20%, which we said in the graph, you see that is 25%. More than 20%, you can trip instant because it's gonna harm your device. very kind of like harshly. Are we good? So now the IEEE basically defines those non-ideal protection situation that we call the fault right through. Are we good? Now these are the points. Between those points is linear. So for example, we said 45 to 65 is like a step kind of like situation. Are we good? Now, we already mandate the DERs to keep connected to the system. Now, what is that we keep connecting that fault right through, we say voltage regulation modes, okay? What is the full control that we have to implement to kind of like go through that period of time? We said we had before in the previous slide, we said we wanted to like control. There is three options that we wanted to like control in fault right through: voltage level, reactive power, and power factor. That means, okay, we have to optimize the situation to keep the power factor in constant mode. Okay, this is one of the application, one of the requirement that we have to add to our control system. We have to control the voltage by voltage VAR control system, because if we inject or consume reactive power, we're basically controlling the voltage. Okay. Combination of these two, controlling the relation between voltage and reactive power and constant power factor, means that we have to already control the relation between watt and watt, active and reactive power. So we keep the voltage regulated, at the same time try to optimize power factor. Again, it could be implemented by another perspective, voltage watt control. When you control the voltage, meaning basically you are controlling your reactive power, but at the same time you're controlling the active power, the watt, so you keep the power factor stable. The IEEE standard not only have the definition for how long you have to tolerate the deviations, certain deviations in the voltage, but also it provides a requirement for reactive power. Why we have to like have that? Because it's not like we have an infinite amount of energy in our resources, and if the system would consume like infinite amount of reactive power, we are good, and a large amount of reactive power, we are good, and the system could be connected and inject whatever amount of reactive power that the fault demands. Now, there is a cap, and it's understandable. So, in order to deal with that limitation, we add another requirement. So, yes, the inverters have to have connected based on those graph of the voltage duration that we saw, or that table. But the requirement also says there is a maximum minimum reactive power, or to be precise, the minimum reactive power injection, okay, to the system. So we cannot just get connected to the system. We have to contribute to the fault. The maximum reactive power is basically defined by the limitation of our resources, but we cannot just connect to the grid and simply not contribute to the fault. There is a minimum contribution expected for all the resources. And IEEE 1547, actually, you could see in the graph, defines that minimum contribution or reactive power injection. Are we good? Now, let's say we had a fault, we stayed connected, we followed the rules of fault right through. Now the fault is clear. How we can get to the nominal situation, okay, from the fault right through situation? We don't expect, same as like in the same logic that we didn't expect or like we mandate the resources to contribute to the fault and do not disconnect it. With the same logic, we say, okay, now that the fault is cleared, we are gonna come back to the regular situation. You don't need to instantly come back to the regular situation. We need to define a recovery method to also protect the DERs from such a vast differences. That is called recovery time requirement, defined again by the standards. So what happens is that, as you can see here, at this point, the fault is cleared, but we don't expect the voltage to instantly go to the no trip zone or like the or to the nominal voltage. We allow the steps to get to that point. Anyone can tell me what would happen if I instantly change to the nominal voltage, like, or we instantly change to the nominal voltage after fault is clear? What was the role of protection system? The role of protection system was to see the deviations, and deviation was percentage wise. Okay, to see the deviation is per unit and react to the large deviations. Now, during the fault right through, we actively change the control or the protection threshold. So now if we instantly wanted to go to the nominal voltage before the fault, what protection sees is a huge overvoltage. So it's considered as another fault and trip. So we want to like ease the way of the DER into the steady state, into the system. Make sense? Now, let's summarize what we talked about the standard actually. We said we need fault right through. We said the fault right through has different settings with the ideal protection setting. IEEE 1547 basically defines those lines of expectation from the DER. Defines the voltage right through, defines the regulations times, and the power exchange requirement during the fault. Which could be high voltage right through or low voltage right through, swell or sag in a voltage. It basically introduced a supportive control system or the requirement for the supportive control system. So we could enhance our current control system. For example, in your own model, you have a Drupe control or a PID for grid following, or a PID PLL control that works with the ideal situation. Okay, now we adding another logic by this standard, so they have to contribute to the fault during the fault right through. And this is not just the voltage and reactive power and power factor regulation. There is a timing factor too. So we saw in the graphs that, okay, it's not just tolerating 20% voltage sag. We are tolerating that for a certain amount of time. After that time, we don't have to tolerate that. We could trip. Are we good? Now, that being said, I also added several video. I posted several video in Canvas page, okay, to for you to get another perspective, another description of fault right through. Okay, and since your assignment 4 is based on fault right through analysis, okay, I added a step-by-step guideline. In a way, I posted that in Canvas, step-by-step guideline, that how you can change your current control system in order to be able to do fault right through. So you have your Drupe control. How can I change it so it would be able to do fault right through? It's a step-by-step guide, but it's not, I want to be honest with you, fault right through is a very kind of like novel topic. Okay, but when I say novel, that I don't mean that it's like invented like 2 years ago or like 5 years ago, but there is a very limited amount of content over fault right through techniques. Okay, so it is a little bit hard for you to search and find the materials for fault right through. That being said, reach out. If you have any problem for any steps of the assignment 4, email me, reach out, we could work it together. Okay? Now, this is so far our contest. Now I'm gonna give you, like, I don't know if it's considered as a good news or bad news, but this is our last session. Okay, today was our last session of lecture. By today, we pretty much covered all the concept that we wanted to cover through the semester. Okay, so next week and the week after that, which is before that week, we don't have any sessions, but I encourage you to dedicate this time for your assignment 4 and your final report. Okay, again, reach out for if you had any question or any difficulty to do those tasks or those assignments. The bad part of the news is that we don't gonna see each other regularly, and I'm gonna miss you, and I know you are gonna miss me too. So yeah, so that's kind of like the situation. Is there any question? Go on. When the fault happened, all the fault right through that we talked about, okay, was during the fault. So a short circuit, for example, happened in the system until we fix that short circuit and we back to the normal situation, we have a fault period. Fault right through is for that part. Now, when the fault is cleared, meaning now there is no such a malfunction or disturbance in our system, system could go back to its previous situation, normal previous situation, a steady state situation. But we don't go instantly, because if we go instantly, it's also would be considered by a system as another fault or another overvoltage. Do you see what I'm saying? So like for example, in a fault, this is the timeline. Okay, this is the timeline. This is when the fault happened. This is when the fault is clear. Okay, here you have a certain amount of P and a certain amount of Q. When the fault happened, you need to increase the Q, meaning the P is decreased until here. When the fault is clear, now the system doesn't need that Q. So you need to increase the Q. If you do that instantly or instantly increase the active power, it's basically the control system will see it as the rush of a new car, which the situation is the same as when you have a fault. So the protection system would also see that as another fault happening. So what you're gonna do is to, okay, ease our way into the steady state situation. So we are gonna come back step by step. So let the system adapt to the new situation. The IEEE, there's several standards. You could see that there is like a NERC standard. This is the red line. There is a HECO standard, green line. The PREPA standard, like the European countries like Ireland has their own standard. This is like the yellow line. The IEEE one that I mentioned is the black line. So it defines how you have to change until you are in a nominal voltage and how long each step would take. Makes sense? Or like example, like uh, uh, you see the American versions like IEEE and NERC doing a step by step. Okay, but if you look at the pre-pay or Ireland situation, Ireland standard, they are going linearly. It's not a step by step. They are increasing voltage linearly until they are in a steady state situation. There is no kind of like better or worse. It's just regulation based on their own system. So they analyze the system. Like in Ireland, they said, okay, it's better for us to go linear. In the United States, they decided, okay, we analyze that, we optimize the situation. It's better to go step by step. There is no kind of like this one is better, the other one is worse. Are we good? Any other question? No? Guys in the Zoom, no question? Okay, thank you very much. So we are finishing our course basically today, and have a great rest of the day. Do not hesitate to contact me if you have any question or any uh, problem fulfilling the assignment or the final report. Okay? Good.